Time is the cylinder's worst enemy. Cylinders deform over time, like that bumpy blue amberol we just saw. Cylinders decompose over time, initially degrading the recording and ultimately destroying the carrier. Over time, improperly stored cylinders can become compromised, like this Francis Densmore recording, to which the legacy cotton batting is stuck. The longer we wait to preserve our cylinders, the more time they have to deform, decompose, and suffer damage in storage and handling. I'm a collector and historian of early recordings, and over the years, I've examined countless artifacts in both private and public collections. Far too often, I've witnessed the irreparable impact of time on cylinders. I'm sure you've seen it too, and you know it's not pretty. Managers who find such carnage in their collections inevitably want to do the right thing, which is to preserve cylinders now before they deteriorate further. But that's easier said than done, because even when the money's available, cylinders can pose a unique set of challenges. So what do we need to know in order to do the right thing? Let's begin with a quick review of cylinder audio recordings and the technologies that allow us to preserve them. We are incredibly fortunate to have two complementary transfer technologies at our disposal: optical and tactile. Tactile methods are adopted from analog technologies developed for grooved disc playback. We use LP cartridges bearing gemstones polished to specific geometries, lightweight arms and linear tracking, A to D converters, and other mature technologies that everybody's familiar with. Like Helen Keller, tactile methods explore the object with a light and precise touch. Optical transfer methods don't touch the object at all. They map a cylinder surface using reflected light, much like a digital camera. And in fact, it's the image from the scan that's actually the archival preservation transfer master. Sound is derived from the image using a number of algorithms and conversions. In other words, the WAV file is a derivative. How do we determine which of these technologies is most appropriate for a cylinder or a collection? I think 5 criteria pretty well inform our assessment and guide us to the right decisions. Those 5 criteria are the capability of the technology, its throughput in a production environment, the cost per transfer, the audio quality of the transfer, and the risk to the carrier. The first criterion, capability, is the unique competence of a technology to preserve a recording. For instance, optical methods are just fantastic for reading a misshapen carrier that a tactile method cannot. I mean, like this experimental talking doll cylinder from 1888, this twisted mess which was found in the desk of Edison's personal secretary. That's pretty amazing, right? That can be played. This was scanned a few years ago on Berkeley's prototype. Now there's a production version for hire at the Northeast Document Conversion Center. Over the last couple of years, I've pointed several items from both public and private collections to NEDCC. I've taken some of my own holdings there, and I have to say it's a most impressive operation. They've made the investment in equipment and in software. They've dedicated an optical scanning room. They've trained and maintained an engineer. They offer this as a service for hire to both public and private collections. Optical is certainly the way to go for terribly deformed and broken cylinders. Fortunately, most cylinders in our collections are still relatively round and intact, which brings us to our second criterion, throughput. How quickly can a collection be processed? Throughput depends on the type of cylinder at hand. Let's take as our reference a common 19th century cylinder recorded 100 tracks to the inch at 120 RPM. Throughput also depends on our digitization standards. Let's adopt the 96 kilohertz sampling frequency, 24-bit word depth, as specified by EASA TC04, the standard we all live by. By holding these parameters constant, we can make apples-to-apples comparisons across tactile and optical technologies. Tactile transfers are done in real playing time. The recording on this cylinder is about 3 minutes long, so once mounted on the mandrel, it'll take 3 minutes to digitize. In contrast, scanning does not play the record in real time. Its clock time is a function of the number of samples taken and the speed of the cylinder. Given these specs, optical will scan this particular cylinder in 88 minutes, or just under an hour and a half. Now, I should note that NEDCC recommends scanning at a sampling rate of 48 rather than 96 kilohertz. At this resolution, the scan would take only 44 minutes instead of 88. And on their system, there's also an option to quadruple sampling density across the width of the groove. That, unfortunately, quadruples scanning time to around 6 hours. And while it does offer advantages, as we'll see in a minute, it does not bring the scan any closer to TC04 compliance. So for the sake of fair comparison, we'll stick with the 88-minute scan time. Let's normalize these throughputs to an 8-hour day, allowing time to mount, calibrate, review, do all the other things that have to be done between scans. An optical engineer can complete 4 transfers in a workday, or +1 if left to scan overnight unattended. That's 5 transfers per day. Tactile engineers report transferring between 5 and 10 cylinders per hour. Taking the average of 5 and 10, which is about 7.5, a typical engineer can sustain around 60 tactile transfers a day. Now, of course, these are ideal throughputs, and they are encumbered by extra duties, such as photographing the carriers, entering metadata, processing derivatives, attending meetings, all the things we do. But as these responsibilities are common to both transfer methods, they pretty much cancel out and leave us with a 60-5, or if you prefer, a 12-1 differential in throughput. So how does this translate into cost? Well, cost is a function of throughput, so we might estimate an optical transfer to be about 12 times the price of a tactile transfer. But optical units are more expensive to acquire and operate, and those higher expenses, amortized over lower throughputs, kind of increase the cost differential. Exactly how much depends on how you're going to approach it and how the proposals come in, I guess. But for now, and for a collection that can be preserved by either technology, we might expect optical preservation to take about 12 times longer and cost at least 12 times more than preserving the collection via tactile transfer. Now, there are times we would readily pay such premiums. As we saw earlier, how else would we salvage deformed or broken treasures that would otherwise lie mute? And for many cylinders, we might gladly pay a significant premium if we knew we could get a more accurate transfer to satisfy our most demanding archival requirements. So that brings us to our 4th criterion, audio quality. TC04 specifies that we gather audio measurements with 24 bits of resolution. The greater the bit depth, of course, the higher the audio quality. What kind of bit depth is delivered by each of our transfer options? Recall that optical transfers visually map the recording's surface. Here's a depiction of a cylinder being scanned. The waves are the recorded sounds in the grooves. The lines are the optical probe's measurement of the groove height. So across the full range of the probes that are being used today, scanning can measure up to around 4,000 discrete values of the signal's height. That's 12 bits of optical resolution. In actuality, however, a cylinder's undulating groove is really, really shallow, typically only 10 or 12 microns, top to bottom in its excursion. In this very narrow range, the scanning probes in use today can resolve only a couple hundred levels of amplitude. That's about 8 bits of optical resolution. 8 bits of optical resolution translates into 8 bits of audio resolution. Converting the image data into sound is done with really sophisticated mathematical formulas and transformations, but no matter how sophisticated, no mathematical transformation can yield a greater accuracy than the data it's based on. 8 bits in, 8 bits out. In practice, given the limitations inherent in the technology today, optical is an 8-bit system. This fact can be obfuscated when an audio file from an optical scan is delivered as a 24-bit wave. We should either leave the audio file at 8 bits, native resolution, so that the limitation is obvious, or we should note the optical bit depth in our metadata, because any audio precision implied above 8 bits is condemned, unfortunately, by the immutable laws of physics to be just noise. Again, 8 bits in, 8 bits out. To complete our comparison, we note that tactile workstations can fall a bit short of TC04's standard as well. But that said, any decent workstation can deliver at least 20 bits. So the inherent limitations for our two transfer technologies today are 20 or more bits for tactile and 8 bits for optical preservation. But sampling rate and bit depth aren't the only measurements of transfer quality. We hear a lot about how one technology may promise less distortion, better linearity, higher signal-to-noise characteristics, or other specs. But in all of this, let's not forget the basics. Basics that are so basic that we assume them in our work every day. We don't even think about them. And let me offer you an example. It's really basic that any archival preservation hardware will not inject invasive noises into the audio, right? That's not in TC04, it's assumed. I mean, if you're making a transfer and you're listening and Rush Limbaugh starts to leak in from the nearby AM station, right? Or a trucker slams in on his CB, that's happened to everybody. Or you hear 60 cycle hum, what are you gonna do? You're gonna stop. You're gonna check your shielding, your grounds, whatever it takes, because this isn't acceptable. This isn't up to archival standards. We're familiar with these invasive noises in the analog domain. What we're less familiar with are invasive noises in the optical domain. Here's a spectrogram from a recent optical transfer of an early cylinder. I know it's hard to read, so I'll go through it with you in a minute. But I will confess right now, it's also hard for me to show this because it reveals problems that are prevalent and unfortunately unacknowledged in today's optical transfers. As I said earlier, we all want to do the right thing. And right now, the right thing is to recognize and address the issues made obvious in this simple spectrogram. I mean, it's really disheartening to see optical transfers containing phantom noises, broadband swishes, and other invasive noises that I will emphasize are not on the cylinder. So as we assess the qualities of any preservation system striving to meet our highest standards, it's critical that we listen to transfers that are made in production settings. And any discussion of potential performance in some theoretical space doesn't count. To this end, Indiana University has begun a rigorous and independent assessment of the sonic qualities of the leading optical and tactile systems. I expect the results of this study will help all of us make better informed decisions. In a few minutes, John and Nick will demonstrate what high-quality tactile transfers sound like. But before they do, let's address the criterion that rises to the top of many lists, the well-founded concern about risking the carrier in the earnest attempt to preserve it. It's a balancing act, isn't it? I mean, how do you balance the ongoing deterioration of your collection and the urgent need to preserve it with the fear that you might damage the artifacts while you're preserving them? The generally accepted principle is that optical scanning is the choice for recordings too delicate to touch with a stylus. And that's a very good principle, although it doesn't identify which cylinders might be too delicate to touch. Fortunately, that's an easy triage for us to do, and let's go through that right now. Bill Klinger estimates over 1 million cylinders survived into the 21st century. Did I get that right, Bill? It's at least that many. More than half of these cylinders are molded in celluloid. Edison blue amberols comprise the bulk of this type of cylinder, and others boast names like everlasting and indestructible. As you can see, celluloid cylinders are tough. They were engineered to be played with a stylus bearing more than 50 grams of weight. They're so tough. Edison had to use diamonds as styli because the celluloid wore out sapphires. These records can take a beating. Another 40% of surviving cylinders are also molded, meaning their audio information is pressed into a pretty hard surface. Not as hard as celluloid, grant you that, but pretty hard nonetheless. These were engineered to be played by styli bearing 25 to 30 grams of weight. Here we see a molded Columbia cylinder under an Edison Model C reproducer. Records like this are pretty tough too. A modern tactile mechanism generally tracks between 2 and 4 grams and is way more compliant than any period reproducer. Relative to what a molded cylinder was engineered to withstand, a polished stylus in a modern mechanism is as light as a feather on a midsummer's breeze and poses no practical risk. The greatest risk, a risk that's shared by both tactile and optical, is human handling, as we saw earlier. Of course, optical can preserve molded cylinders too, but given the overwhelming quality, throughput, and cost differentials, tactile transfer is the appropriate preservation choice for more than 90% of the cylinders in your collections. So what about the rest of our cylinders? Instead of being molded into the carrier, their sounds were directly cut or incised into the surfaces. Most cylinders of this format are commercial entertainment recordings duplicated at the factory, or duplicated by dealers, or duplicated by pirates back in the day. Major archives have successfully preserved thousands and thousands of these cylinders with tactile workstations, so they're certainly not too delicate to touch with a stylus either. What's left, significantly less than, 1% of all surviving cylinders are the one-offs. These would be the very earliest commercial recordings, and it would include any incised recording not made for commercial purposes. Each one of these is the very artifact that originally received and registered the sounds. Virtually all field recordings made before the advent of disc, wire, and tape are of this type, as are the recordings made by phonograph owners in their homes. Each record is a master. Each record is unique. Each record in its own way is a treasure. Are these cylinders too delicate to touch? Last year, a master's candidate at NYU's Graduate School of Music Technology studied this very question. Now an NYU graduate and professor, Rebecca Feinberg is here to premiere her findings. Rebecca?